to our first HEPEC seminar of the semester. Today we're very happy to have Keeley from UC Irvine. Ryan did his undergraduate in Caltech and then moved to UC Irvine to work with Keeley on dark matter and dark energy. And he is moving to South Korea to start a postdoc in the Korea Astronomy and Space Science Institute. So he's worked on previously on self-destructing dark matter very recently. He was involved in a paper that studies the expansion of the universe using the history of the universe using a wide source of data. So if you're interested in that, you should definitely meet us after seminar to bug his head. But right now I'm going to talk about what we can learn from the possibility of dark matter being a source of gamma rays from the Galactic center and dwarfs.
Hello, hi, thank you. Yeah, thanks for having me. Today we're going to talk to you about the Galactic center excess and the complementary lack of signal from Milky Way dwarfs. From the velocity dispersion of galaxy clusters to rotation periods of galaxies, to CMB, and to lensing signatures in cosmological scales, we all know that dark matter has to exist. There are numerous ideas of what it can be, but with a so far lack of a confirmed signal, we essentially don't really know. We don't know what. I mean, we have a lot of ideas, but we don't know what it is. There's for every idea of what it could be, there's a bunch of constraints. And one particularly useful way to get constraints is by using indirect detection. Specifically because we know that it exists cosmologically, and indirect detection, indirect detection assumes, I mean, not assumes, but it takes advantage of the fact that that because it's cosmologically abundant, should there be any sort of annihilation signal, or I guess more generally, any sort of dark sector talking to the center model, any sort of signal should go as we'll take advantage of the fact that that dark matter is cosmologically abundant. And so for my talk right now, I'll be focusing on this blue part of the. And as I understand it, a lot of the research here is done in both, I guess, green and red. So I guess everything that I talk about will be complementary to all of your research. Okay, so like I mentioned, indirect detection can be a useful source of constraints or possible signals, and so thus was the Fermi gamma ray satellite built. So the Fermi gamma ray satellite looks over the entire sky and is sensitive to gamma ray energies from around a few hundred MeV to hundreds of GeV. And the interesting thing is that when the Fermi telescope looks towards the center of the galaxy, it sees an excess of gamma rays. And this excess of gamma rays the presence of it is statistically robust to variations in the background and has become known as the Galactic center extended excess. Here we see if we take everything we know and subtract out those templates, this is the gamma ray residual, and any sort of model dark matter expectation roughly matches it. And so the reason why this GCE is interesting is because it matches the expectations of dark matter annihilation in 3 key lines of evidence. The first is that the spectra of this excess matches the expectations of a tens of GeV annihilating WIMP, annihilating either through BB bar channels or tau electron channels. 2, that the spatial morphology of the excess, as you can see here, roughly matches the templates from what you would expect from dark matter annihilation, namely an NW squared profile. And 2, the total flux of the signal is consistent with the thermal annihilation, the thermal relic cross section, which which would mean that if the signal were to be confirmed to be coming from dark matter, these WIMPs would make up essentially all of the dark matter. Okay, so even before this signal was discovered, it was pointed out in the literature that any potential dark matter annihilation signal could be confused with pulsars, specifically because they have a roughly similar spectrum. Pulsars are typically categorized or parameterized by a log parabola spectrum, and because they can match you can essentially, for any dark matter match, you could choose parameters for a log parabola such that the peak and the high energy tail are essentially matched and are indistinguishable. And so because we do see this excess, it's just by looking at the excess alone, it's unclear if this is coming from dark matter or if it's coming from some unresolved millisecond pulsars or some other unknown astrophysical source. Okay, and so the next most natural place to look for dark matter and to hence answer this confusion about whether this JCE is actually coming from dark matter or coming from an unresolved source of some unknown astrophysical source is to look for a complementary gamma ray excess coming from the Milky Way dwarfs. And so when the Fermi Space Telescope actually does look at these, it sees no significant excess. There are two so far at least, small excesses of gamma rays, but they're not particularly they're not hugely significant. And so with a lack of complementary signal from the dwarfs, we can then place constraints on any dark matter annihilations constraints, and conceivably, we can then test about we can then test whether that's consistent or inconsistent with a dark matter interpretation for the GCE. Okay. So the gamma ray sky is typically a very busy place with numerous point sources, numerous gamma rays coming from cosmic ray propagation through gas clouds in the Milky Way disk and galactic center. And so a lot of this work it involves trying to carefully account for where each of these gamma rays are, essentially categorizing very well what we do know about the astrophysics, so that we can then be very sure about any sort of about the, I guess, morphology and spectra of any excess. Okay, so to this end, we use a software called Galprop, which, like I described, is essentially models the spatial distribution of all the known gas clouds through the galactic center, and then calculates the cosmic ray propagation through those gas clouds, and then from there we can calculate what the expected templates for various physical processes would be. So the most important ones would be Bremslung radiation, pion decay, and inverse Compton. And so then we can then, when we're accounting for the actual results from the Fermi Space Telescope, we can then, so the process to find any excess is to then, for each energy bin, you allow the flux of each of these templates to vary such that it minimizes any Poisson likelihood. And then if you then add in some additional NFW squared templates, you could then for an array of values for that NFW squared template, you could minimize all the other templates around that, and so then the result of which would be a likelihood profile for any for this NFW squared template, which we can then interpret as possibly coming from dark matter or not. So this blue here with error bars is that result. So for each energy bin, we essentially have a likelihood profile, and these error bars, I mean, the likelihood profile doesn't necessarily need to be Gaussian at all. So these error bars are then just whatever the one sigma deviation from any maximum likelihood for that bin. And so it's this quantity that we're trying to interpret as possibly coming from, so I mean, this is the GC excess as modeled by these components. And it's this thing that we're fitting to when we're trying to calculate any sort of dark matter, like best fit dark matter annihilation, dark matter mass or annihilation cross section.
Actually, can I have a question? So when you say like a template for those three components, like do you like, is that a template for like a fixed set of Galactic parameters? So I mean, sometimes this template is a little bit.
Yeah.
Little
So
bit
I mean, so yeah. So that's right. Any one template would be for I guess a fixed set of parameters. In the past, work has been done to explore that space. For my specific work, I took what was found to be the best set of Galactic parameters, or I guess the templates that resulted from those, and went from there.
Okay.
Yeah. Okay. So in general, any sort of dark matter annihilation, any flux coming from dark matter annihilation should scale as the density squared, this J factor, times the cross section. This here is the per annihilation spectrum, which essentially just get from, I guess, it's a result from Pythian. So this density squared, this J factor, is essentially the integral over some region of interest here, integrated through the line of sight of the density squared, and to parameterize any uncertainties in this J factor, we take the density squared to be modeled by an NFW profile with I guess a generalized NFW, in that we allow the inner slope to be different than 1. So the three things the three parameters that we marginalize over when we're doing any of these, when we're calculating any of these posteriors, is we marginalize over the local density, marginalize over this gamma, and marginalize over the scale radius. This gamma that we get is coming from the actual Fermi gamma radiated themselves. So because we see because we see the residuals follow a slope that would go like 2 gamma, we can then specifically measure it there, and then use that information as a prior when we're deriving a prior for the J factor. Similarly, we get the scale radius from simulations, essentially a concentration mass relation, and the local density here is derived from looking at the vertical motion of K-Dwarfs near the solar position. That's, I think, a useful way to calculate the local density, since it doesn't require, the alternate way to do it is by using rotation curves, and there you would need to essentially do a projection from, I guess, looking at the rotation curves from beyond our solar position. So that's sort of, I guess, any sort of inference like that would be model dependent, but here it's a more direct measurement of what the dark matter density is close to our actual position. And so by doing that, we can then take each of these parameters to be essentially independent of each other, since they're coming from three different constraints. And so then any sort of prior on the J factor is just the convolution of the priors of each of these individual parameters. Okay. And so then if we have gamma ray data. We have the actual gamma ray data for each energy bin. We have the J factor for each of these, and so the only thing left is to then we can calculate essentially a posterior for the dark matter mass and annihilation cross section, which is what is shown here in orange with the 1, 2, 3 sigma contours. So this is for the galactic center, or I guess I'll come back to this. Here we can then perform the same calculation for the dwarfs themselves. The Fermi team has released an equivalent set of data products, which are essentially flux limits in energy bins, and so we can perform the same calculation as I described before. And here you can see the tension, at least qualitatively, where the region preferred by the galactic center is essentially the same region as excluded by the dwarfs. And then to be a bit more precise about what I mean by the tension, I calculate what I call an evidence ratio, this ER. This evidence ratio is, it can be thought of as a base factor, where the model for the numerator is essentially the same as the model for the denominator, except that the numerator model has 2 copies of the parameter space, and each of those parameter spaces describes describes one of the data sets independently. So you can think about this as whether or not, for a given model at least, whether the 2 data sets are very independently of each other or have some mutual information. Like if P of D1 and D2 is different than the product of D1 and D2, then they have some mutual information. So here, if the evidence ratio turns out to be greater than 1, then the data prefers to be described by 2 sets of parameters. If it's less than the 1, the data set's prefers to be described by 1 set of parameters, and if it's 1, then there's no mutual information. So when we look at BB bar and tau channels, we get very large evidence ratios, which if you use any sort of standard Jeffrey scale, which would have a base factor of 10 being some sort of strong indication, a factor of 100 being some decisive indication, a factor of more than 1,000 is beyond decisive. So, using these statistics, we can clearly see that that for both BB bar and tau channels, there is this meaningful meaningful tension that should be pointing to something other than dark matter as an explanation, or at least other than the simplest dark matter models as an explanation for the GC. Okay.
So do I interpret those green things as excluded regions, or
so it
or
should be again the
signals?
1, 2, 3 sigmas.
1, 2, 3, like they're excluded regions. Sorry, not like.
So
not sigma. Are they? Actually, you tell me what are the greens again?
So it should be a posterior. So this contour between the darkest and light darkest should be, I guess, like a delta log likelihood of, I think it's, 3, 6, 10 for these regions. So
this comes from like fitting like all of the gamma ray data from all the dwarfs together, or
yeah. So each of these green dwarfs.
So like interpreting it as a signal. Is that what you're saying?
Preferred region.
Interpreting it as a signal, that's what you get, the green.
I mean, it's a posterior. So I mean, I guess.
Okay, I think we're at.
Must be the yellow region.
Yeah, I think that's what you're saying. Yeah.
So yeah, so I guess the simplest takeaway is that anything above the green should be excluded. Anything below should be preferred or less excluded.
Yeah, I guess I'm asking a philosophical question. What's the difference between like excluded and evidence for a signal? I think you're saying for the green, you're saying it's. Well, I guess it doesn't really matter.
So I mean, I guess one way you can think about this. So if I were to extend this further down, a signal should go to essentially 0 likelihood as you go further down, and essentially this stays like roughly constant in that. Anything further down is essentially equivalent likelihood to here.
Okay.
So I presented arguments for why I don't think, at least for the simplest models, that it could be for dark matter as an explanation of the GC. And so then the next question to ask is, to what extent do we see the same tension or not see the same tension for astrophysical type models? And two common parameterizations for the spectra of these astrophysical models are either a log parabola or an exponential cutoff. Okay. So when we're talking about the astrophysical models, I generally think it's important to try to ask two questions independently. One, how well do the normalizations of these models, how well do the scaling relations of these models explain the presence of a signal from the galactic center and the lack of a signal from the dwarfs. And so that's primarily a question about any like the Fox scalings or normalizations. And then the second question would be, how well do these models in themselves explain the specific spectra of the GC? And so to make those two questions essentially independent, this n naught parameter, which is just this, which is just the normalization of the per annihilation spectra and not the total flux spectra. I essentially choose n naught such that the integral over the entire energy range is equal to 1. So so then this alpha beta here, or this gamma and cutoff scale, essentially just describes where the photons in this whole energy range are distributed into bands, as opposed to correlating these parameters with any sort of total scaling relation of the signal. Okay, and so if we then set that, we can then put in any sort of scaling relationship by hand. And so for astrophysical systems, I then argue that it makes sense to parameterize it to say that any flux signal should scale as the stellar mass of the system. And so we could then, analogously, we could then say that this, the stellar mass of the system would be analogous to the, I guess, m star over the distance squared would be analogous to the J factor. And this combined parameter n dot over m naught would be analogous to a cross section. Here, the point is that this parameter should be consistent across various systems. Should be in general some sort of property of if it's pulsars, a property of pulsars, or whatever the astrophysical specific astrophysical interpretation would be. And this thing would vary between regions. And so hence, if we're trying to say any sort of signal is consistent, we're looking at this thing and marginalizing over this J factor equivalence. Okay, and so then when we calculate this evidence ratio for these two for these astrophysical models, we get something that's essentially less than 1, in that they essentially prefer to be at least by some small significance, prefer to be described by the same set of parameters. And when I say some small significance, it's the same significance as any sort of small overdensities from the dwarfs. So maybe coming back to your original question, if the signal from the dwarfs is an actual signal, then this cyan line should go down towards 0 quickly. But if this levels off towards, say, like 0.3, then that's a measure of the significance. And so this small significance overdensity, because it's because it picks up the same scale as the scale picked up from the GCD, that fact essentially sets is what's driving these evidence ratios to be less than unit. Why there is mutual information between the two data sets at all. Okay. And so I guess one more point. So if these small significant overdensities of gamma rays from these dwarfs were to become more significant, then these evidence ratios should only decrease, and any sort of any conclusion pointing towards an astrophysical interpretation of the GCE, or I guess the combined data of the of the Galactic Center and the dwarfs, should only become more significant. Okay.
So actually, I have a question. So
yeah.
You're basically, so for your dark matter, you basically effectively have two priors for the dark matter. One, it's like the flux scale is like 1/r squared, and the dark matter's mass is, or the J factor, whatever, is in some way proportional to the stellar mass.
So for the astrophysical systems, or
what's that?
So for the astrophysical systems?
Yeah.
So I mean, I guess in this case, that would be like saying any sort of, so the 1/r squared thing would be saying that any sort of source for these gamma rays is, and we're essentially beyond where that distribution would exist. Okay.
So I guess I was just going to say, like, if the stellar mass in some way doesn't scale like the dark matter mass, or it just looks like a lot of scatter in that, does this prior break in some way, or?
So I mean, with these, I mean, so this has nothing to do with like a dark matter particle mass.
No, but no, the halo mass. I'm assuming you're saying that the mass in the stars is a proxy for, like, you know, the mass in the dark matter.
So I mean, I guess I was thinking along the lines of, if you have some sort of total stellar mass of some dwarf, say, then some fraction of those would be pulsars, and then for each pulsar, there's some fraction of that would go into gamma rays, And then I guess the assumption there is that for various systems, each of those fractions are at least roughly similar, so that we could then say that the scaling is at least roughly correct. I mean, conceivably, if IMFs change very much from region to region, then that would break down. But I mean, there's at least no observational evidence for particularly strong variations in IMFs. So, I mean, it seems roughly valid at like 0th order. Okay. So I talked about simple dark matter models, and I talked about the scaling relationships for astrophysical type models. In principle, then you can go one step further and say what would more complicated or perhaps more realistic dark matter models, how would these models fare for this question of attention? And so there's potentially infinite numbers of ways you can do one-parameter extensions to any simple dark matter model. So I'm going to more specifically talk about a representative SIBM model. So the idea with this model is that any of the gamma rays would be produced by an inverse Compton process, and any sort of dark matter annihilation would produce as far as the gamma rays are concerned, would produce high energy electrons, and these high energy electrons would upscatter any component of the interstellar radiation field producing gamma rays. And here you see, I guess, that's essentially what I've written here is an equation that the rate of change of the gamma rays with scale is as this inverse Compton process. Okay, and then if you're looking for the total per annihilation spectra for the gamma rays themselves, it would then be a distribution of the distribution of this interstellar radiation field, the distribution of the electrons produced, and then I guess convolved with this inverse Compton process. Okay, and so then when you do that, you can then determine what the total flux spectra would be, and you could then say that it scales more like a 3-body process, whereas before for dark matter it scaled just as like n chi squared, but now you have it being proportional to again any sort of density of any sort of interstellar radiation field. And so here, for this representative model, at least, we have essentially an additional scaling than with a simple dark matter model, where again we see the flux of any signal scale is scale with the stellar mass of the region. So this essentially allows us to a perhaps natural explanation for why you would see essentially with a bright interstellar radiation field in the galactic center, why you might expect to see gamma rays coming from there and not to see any complementary signal coming from dwarfs. Essentially because the stellar mass there would be greatly different. Okay, so then if we calculate the same evidence ratio for SIBM, we essentially get a number that would be that's essentially unique. That there's with this scaling relationship for this representative SIBM model, there's no real mutual information between the dwarfs and the galactic center. Okay. Similarly, we could, like I mentioned before, there's sort of two independent questions about whether about this tension, which is primarily a function of the total flux of a signal, and then we can also ask how well these individual models can explain the GCE itself. And so to that specific question, I calculate what's a more traditional base factor, where the difference in the models between the two numerator and denominator are like actually different models instead of the same model with different with copies of the parameter space. And here we see essentially results where we see that the even beyond this question of the tension, any sort of astrophysical interpretation here called log travel and expression of cutoff, they can explain. They have these large factors. They're very many times better at explaining GCE itself than either than either the dark matter models. So each of these are normalized to the BB bar. So so that's why it's not included here. So essentially BB bar is 10 to the 24 times better at explaining it than tau leptons, but 10 to the 12 times worse than explaining it than a Mach parabola. And when you look at the actual data, you can sort of see why. Here in green is the tau leptons, and essentially for our data itself, tau leptons have trouble explaining both the position of the peak and the high tail cutoff. So that's why essentially that base factor relative to BB bar is particularly worse. And here you see at high energies the log parabola and BB bar are roughly the same, but it's really only towards the low energy. Essentially that because the NFW squared profile prefers very little photons in these low energy bins, the log parabola and I guess exponential cutoff can explain that fact better than any dark matter model. And here and essentially the same fact occurs with SIDM, where so like the tau lepton, it's hard for and like the SIDM spectra I wrote down to explain both the high energy tail and the position of the peak. So we essentially have two statistics that effectively show that that astrophysical models are better at explaining both the GCE itself and better at explaining and better at explaining this tension between, or I guess explaining the presence of gamma rays from the Galactic center and a lack of gamma rays coming from the Dwarfs. So I guess this fact, this question of the tension, combined with various other probes looking at the GCE. I guess when I say that, I specifically mean looking at any sort of non-Poissonian templates. So if the Galactic center itself was explained by some unresolved point sources, then spatial bin to spatial bin fluctuations would be non-Poissonian if it's just some unresolved point source. And so a lot of people have put a lot of work into trying to look for any any sort of small scale fluctuations from the gamma ray data, and essentially the result of that is that they do see that there's some sort of small scale power in that distribution, indicating that I guess there's two potential explanations for these non-Poissonian type of things. Either that there is truly some unresolved point source, or that the background models themselves don't include the smallest gas clouds that exist in the Galactic center, and hence not modeling those correctly could generate that. And an additional line of evidence with this whole question of the Galactic center is that there's been a detection of an X-shaped template, and if that X-shaped template turns out to be robust again any systematics, then that essentially rules out any NFW squared template. Both templates would be trying to explain the same thing, and it seems that this X-shape tends to be preferred. And essentially because it's basically impossible for dark matter to explain any sort of template like that in that particular shape, but specifically instabilities in bulge cell populations in the bulge could explain an X-ray template like that. And I guess the reason why it exists at all is because when you look at Y's radio data, you see the same X-rays. I mean, that was, I guess, what initially generated this shape. So there's, I guess, like a strong prior for such a thing to exist. It doesn't come from nowhere. So there's these three lines of evidence about trying to answer whether the GCE is truly coming from dark matter or not. I guess this question of attention, which again seems to point towards astrophysics, any sort of non-Poissonian templates, again pointing towards astrophysics, and this possibly detected X shape, which again points towards astrophysics. So though each of these can potentially have systematics associated with them, because they each independently point towards an astrophysical explanation of the GCE, it seems more and more that.
So the first point is more like a model dependent question. The first point you said is a tau or BB does not do it, it's a model dependent question, because I can come up with a model with a combination of BB and tau, and that would do it.
That's fair. So if you're trying to specifically, I guess, explain these, I guess you could, some combination of either channel should be able to, I guess, better explain the any sort of specifics of the spectra. But I guess I guess the reason why I like the evidence ratio is because it really has more to do with the total flux of the signal than any sort of specifics of the spectra like that. So I would argue that essentially this question of the tension is largely independent of uncertainty in annihilation in branching ratios or the like. So I mean, essentially, if you were to choose some combination of BB bar and tau, both these regions would shift in the same way, hence preserving essentially the scale of this evidence ratio.
That's not, I don't know, is that intuitive? Because tau, see, you are relaxing the bounds for both BB bar and tau if you mix them in a combination. So I would think that it would work in the positive way. No, I'm raising this question because you said for model is saying astrophysics. I don't think it's, unless one does the analysis, one would not know. But the second, the other 2 points could be much more clear. But do you know, like, was the really how much of an astrophysics, like evidence for the astrophysical source is kind of there for the other 2 points? You are saying the unresolved point sources, so that's probably fitting the data much better than even if I bring in BB bar and tau. Is that true?
So, as far as what I've done, so once you essentially do this some likelihood minimization to get this, so I guess once I have this, any specific questions of the morphology or like the spatial bin to spatial bin correlation of photons is sort of already I guess integrated out. So so if you're talking about, I guess, I mean, if it were the case that the non-Poissonian template was very robust, then I would think that would be the most likely line of evidence that would most definitively answer this question about whether if it's dark matter or not. I mean, an equivalent thing is that if you had a higher spatial resolution gamma ray telescope, it could that would be the most definitive way to answer this question. But I mean, until that happens, I think I think at least from a model dependent side, I think so. I mean, so any sort of branching ratio should just occur in sort of this term, right? You could sort of play games where the distribution of where your gamma rays occur in each spatial band, you can modify that a bit to get the total shape of the six signal more correct. And that would very much explain those base factors I talked about at the end. But this question of the tension really only occurs between these two things. And because these things are independent of any specific model, particle physics model like that, I guess that's the primary reason why I say that this evidence ratio should be at least the scale of it, and that it's a factor of 1,000 or so, should be roughly independent of those sort of model uncertainties. Okay, so that's essentially time. Yeah. So this is, I guess, what I would want to leave you with. So if you have any questions.
mentioning astrophysical sources, but it sounds like astrophysics is what you say it can fit the data because the data doesn't fit the dark matter annihilation. But we know a lot more about the astrophysics. We have X-ray maps of the Galactic Center, we have radio maps. There are all sorts of ways of also adding that data into your data set. Have you done that and included other
Yeah,
wavelengths?
so I mean, I guess maybe a bit of the history about how, so that's largely a question about maybe this slide. So I guess maybe the history about how these templates were, I guess, originally made. So the Fermi team itself releases what they consider like a best fit background model, which is mainly which is optimized itself to detect point sources, and then work that occurred before I really started doing this detected specific, like you mentioned, additional, I guess, like gravity along and inverse Compton components that corresponded to these maps in other bands that we're used to. I mean, so you take maps in other bands, construct templates for any gamma ray signal, and then do this Poisson likelihood minimization. And whether if that template has a significance of say like TS of 25 or so, then you say you've discovered a new template there. So yeah, so this work has been done, but all of that has essentially been incorporated into these Galprop models. So, and specifically, I guess, more recently, that's, like I mentioned, that's how the X-shaped template was originally found. You see, like a same X-shape in WISE data, you transfer that same shape to gamma ray data and see if it better fits the Galactic Center signal than some NFW squared profile, and it turns out that it does. So
yeah, I mean, to kind of follow up on that, I mean, one reason that complicates this a little bit is like there's different resolutions for like different wavelengths. So like, you know, gamma rays, the resolution is like ordered like maybe a degree in some case, right? So you can say like, you know, we've resolved like a gas cloud really well in X-rays or something like this, right? But it's then sort of mapping that on to like, you know, how that corresponds to the cosmic ray propagation in another wavelength. That's where sort of a little of this fudginess kind of and these uncertainties kind of come in terms of how to correlate them. Because what you're saying in principle is like, probably, oh, it's, you know, why can't we just say we know there's gas clouds here, and just if something makes radio waves, it should make, you know, gamma rays or something like this as well. But it gets hard because sort of when they're tuning the models, like to fit to say the gamma ray data, right? That the resolution is not nowhere near as good as some of the wavelengths.
I'm sure you've done this, but can't you just go to the higher resolution X-ray data and say, okay, these are all the X-ray sources here, and then go to Fermi and take out the same region of the sky, and then ask if you stack all of these things, is there a statistical excess flux in gamma rays stacked across all of the X-rays?
I guess that depends upon knowing the nature of, like, you know, how X-ray sources, how an X-ray flux correlates to a gamma ray flux, right?
No, I'm not asking that question. I'm just asking the purely empirical question of just do the stacking and see if there's a correlation or not.
Let's see, I don't know how many X-ray sources are going to approximately in the center of the galaxy.
Galactic Center? I don't know how big the Galactic Center is.
A degree or so to me, I guess.
It's like a 10 by 10 degree.
I don't know, but I would.
Oh, and this excess, yeah, this excess in different scales, several degrees.
This is X-ray?
this is gamma ray.
There are all sorts of X-ray craft towards the Galactic Center, cataclysmic variables, stuff like that. So, which may or may not produce gamma rays.
Actually, well, that's one follow-up question I had. Like, you've been talking about like when your astrophysics, like your templates are pulsars typically for a Galactic Center, and you know, like the other templates are like OB stars, like they winds from these things are often like talked about in terms of producing gamma rays. Is that how? I mean, those templates are a little bit different. Like if you read the Fermi Intergalaxy paper, they talked about that type of model. Does that affect anything going on here?
So if you're looking at the so here, I guess when I'm saying that any sort of these astrophysical models are specifically trying to explain flux in each bin for an NFW squared template. I guess the reason why in principle you don't necessarily know if pulsars or whatever would necessarily, and they wouldn't necessarily follow an NFW squared profile, but because this residual happens to follow like an NFW squared profile with like a gamma of 1.1, we're trying to be conservative in the sense that, so if you have some sort of astrophysical model or even some dark matter model where you wouldn't expect the morphology to follow an NFW with a gamma 1.1, then that's already disfavored just from looking at this. So by trying to explain this NFW, the flux corresponding to this NFW squared template, we're trying to be conservative in that sense. If that answers your question.
Okay.
So it was,
Okay. So it doesn't matter in some sense. I mean, the exact shape of the signal doesn't.
Sure.
So usually when you have a log likelihood difference, you expect some chi-square distribution in degrees of freedom, right? So when you're comparing these posteriors, say with the astrophysics and a dark matter annihilation model, in what way is the different number of knobs that are available to take?
So I mean, I think, so typically because maybe this is sort of, I guess, a cop-out, but typically because things are, if you do things in a Bayesian way,
Yeah.
then you don't necessarily need to worry about that so much. I mean, it's all sort of incorporated in
It's folded into the posterior.
yeah. Yeah.
So, when can we say that astrophysics cannot fit this signal? So, do you have what do you need? How what kind of?
So I mean, in some sense, it's right. So like I mentioned previously, if you're talking in a very broad sense, if you had say some gamma telescope that happened to have like a 10 times better resolution, then I think we could be more definitive that, if you then don't see any sort of this underlying population that may or may not be there, then I think we can definitively say whether or not it's astrophysics, I guess.
I guess in principle, if you're green and you're whatever color that was, orange, reddish thing, once they start overlapping, right? In some statistically significant way.
So yeah,
I think I understand what those green things are. Yeah, well, that would, I guess, favor a dark matter interpretation. Right? I guess you need some. Yeah, it's like the dark matter is the sphere and everything else is not sphere, right? It's like your other model, you're like, in the sense. You could come up with a pulsar model, I guess, and do the same thing, right? Because even though, pulsar emission from, dwarf galaxies is probably minuscule, right? It's still not zero, right? Emission, so.
But for pulsar explanation, it seems like you need thousands of them. And in the beginning, I thought that you don't have that much of a pulsar population.
I don't know. I never really bought those arguments actually. I think the Galactic Center is a mess, and I think
so you
it's
can
just,
have thousands of them.
yeah. I think not really. There's we can't have 1,000 pulsars in the Galactic Center. Why not?
Are there any other questions? Okay, well, if you're interested in speaking to the speaker further, we're going to meet. We're going to shoot for the 5th floor main room, because I think the 4th is already taken by the flying group.
We're taking him on a lab tour, so it actually should be open.
Oh, okay.
I don't know when Rubeck's will be.
I think he's meeting 2 to 3, so I think.
Oh, maybe they are.
Yeah, so we'll shoot for the 5th.
No, they might be like, Rupert might be showing his lab
And
or
if
something.
not, we'll just
No,
shoot down the lower
I'm
floors.
showing in the lab
Oh,
at
you're showing
2:30.
Okay.
I don't know when.
Then I'll get
Rubeck's-
And I'll add some slides that will drive September
Yeah,
today.
that's-
Just like this
I
before.
understand.